So let's get started with the solution. Now you can see the tree which I drew before. Well, I have redrawn the tree without the arrows, and I think I have explained how to draw this tree in the previous videos. So now we will see that how we can collect the answer. So as I have discussed in the previous video, that if you track down each branch of this tree, then you will get one specific combination of the items, and for that you will get a price, and ultimately you can take the maximum one of them. But we will do it in a different way. In that way we were going through a branch and calculate its price, but right now we will take the prices from the bottom of the tree toward the top of the tree. Yes. So how does that work? So what we can see here, that when we are at this point in the top, we are actually asking a question that right now we are considering the item that is at index 0 and we have capacity left 10. So what is the maximum price we can get from here? And then we see that we have two ways to go. Either we can take this item or we leave this item. And between the two choices, we have to take which gives us the more profit. So as you can see, if we take the left branch, then we add 7 to it because we take the item, and if we take the right branch, then we don't add anything. And then let's say if we take the left branch, after going to this position, we ask the same question again, that right now we are considering the item at index 1 and the capacity left in the bag is 7, and what can be the most profit from here. Let's say the answer is X, and then we also ask here at 110 what is the most profit from this point, and let's say the answer at this point is Y, and let's say the answer in the point 17 is X. Then what we do actually is we compare X plus 7, because if we go to X then we add this 7 on the way, and Y plus 0, because when we go to Y we add this 0 on the way, and compare between them, X plus 7 and Y. If X plus 7 is greater than Y, then we take X plus 7. If X plus 7 is less than Y, then we take Y. If they're equal, we can take any of them, and it doesn't matter because whatever we do will give us the same value. So if we calculate it a little bit, then we'll get to understand a little bit more. So let's get rid of this pseudo values which we're considering. Let's get on with real values. So actually this 0, 10 will ask both these branches which branch will give them the higher answer, but these branches will also ask the branches below them of which branch that will give them the higher answer, and then it will be built from the the bottom of the tree to the top of the tree. So let's say here, if we calculate quickly, then this 3, 2, this one, it only has 0 and 1 branch, so obviously the answer stored here will be 0, and the answer stored in 2, 2 will also be 0 because there is no other way. But the answer stored in 1, 7 will not be 0. It will either be 10 plus 0, the answer from the left one, or 0 plus whatever the answer here is in 2, 7. So if we calculate it again from below here, so in 3, 2 here the answer will also be 0, and 3, 7 here will have the answer 12, because if you can see that the left branch actually gives you 12 where the right branch gives 0, and we have to take the maximum at any point, right? So we are looking for the more profitable road we can take. So from this point out, this 3, 7 where you are considering the last item, the index 3 and your capacity left is 7. At this point you can get at most 12 from underneath. And now here in 2 7 you calculate that the left is 10 plus 0 and the right is 0 plus 12, so the maximum is 12, so you take 12. And now here at 1 7 in left you calculate 10 0 and in right you calculate 12 0, so what you calculate is 12. And then if we go right here, we don't know the value of 110, so we go down, and here we can see that at 3 0 we will calculate the value 0, at 3 5 we will calculate it 0, and then at 2 5 we'll calculate it 10, because on the left side it has 10 plus 0, on the right side it has 0 plus 0, so 10. And here if we go down to 3 5 it's 0, if it's 3 10 it's 12, because it will take the value 12 here. And then at 210 it will be 10 plus 0 or 0 plus 12, so it's gonna be 12. On 110 here it can be on the left side 10 plus 10, which is 20, and from the right side is 12 plus 0 12, so we take the left one, which is 20. And now at the top the 0 10 it gets from the left 7 plus 12, which is 19, but on the right side it gets 20 plus 0, which is 20, so the answer is 20. So actually what we do is from the child of any node we take the answer that is maximum. So here we take the answer of this branch, we take the answer of this branch, and among these two branches we take the answer of actually this branch here. Here we take this branch, here we take this branch, but here we take this branch, and then here this one, this one, this one, but not this one, here this one, here this one, this one, this one, and ultimately this one. So the red arrows actually mark that from which child the value is coming. And if you look at it, then you will see that in any node, if it has one or two children, it will take the one that is maximum. So if it has one children, it has no choice but to take the value. But if it has two children, then it will take the children with the larger value plus the age that it's traversing. So here you can see that let's say in this node 110, from the left it's coming 10 but plus 10, and from the right it's coming 12 plus 0. So even though the value of the node 10 is lower, but it gets added to the edge value 10, and then it gets 20, and then we take 20 from there. So that's how the tree is calculated, and the answer is 20 from that calculation. So the property of dynamic programming that we can observe here is the optimal substructure one, that at any node the answer depends on the subproblem of that node, but with a different format. So at the very root of the tree we're asking what is the answer for the index considering 0 and capacity left 10, then it depends on the answers of the left branch and the right branch, but they ask the same questions again with different parameters. So this is called the optimal substructure thing. But we also have two more things which are related to dynamic programming, and right now this problem is nowhere close to dynamic programming. The solution is a brute force one where we traverse along every path and we take the maximum one, and the complexity of this solution is going to be very, very high. But now we will actually dive into the solution that will introduce dynamic programming into this, and the two property that is going to be used here is the recurring or overlapping subproblems and the memoization. But how will we do that? Let's see that now. So if you see that there is a term we have seen called that is overlapping subproblems. Now if you notice that some of the nodes have the same values there, Let's say, for instance, we can pick these two nodes, the 3, 5 and the 3, 5 here. They have the same structure and the same subtree below them, but these are copy of each other. So it means that if you know how one of them is going to turn out, you actually know the other one, because they expand as the same tree below them wherever they are. You can also see this tree 2 and this tree 2. The structure of them below them are the same. So what we can do is we can identify them as overlapping subproblems. That means these subproblems, this 3, 2, or you can say 3, 5, they are actually the same subproblem but in different places. So they are overlapping. And that's how we can reduce the complexity of this solution using memoization, as we have seen previously, that if we have overlapping subproblems, then we can use memoization so that we don't have to calculate the same subproblem over and over again. Rather, we can calculate it once for the first time and then store it somewhere, and then later, whenever you have to calculate or ask that question, that subproblem, you can answer from memory. You don't have to recalculate it. So what we will be doing now is that we have to store these questions somehow and the answers, so that whenever asked more than once, you can answer from memory. And the trick is here is the memoization part, that we will use a storage and answer from there. So how we can do it? You can see that each node can be represented as two numbers, the index considering and the capacity left. So we can do this with a two-dimensional array. Let's say this is a two-dimensional array, and the rows are the indexes and the columns are the capacity. So if we go like this, then let's say the rows are the indexes and the columns are the capacity. So if we go like this, slowly creating the array, so we might not be able to draw the full array, but right now let's say we can draw till 9. And if we actually shift it out a little bit on the left, then you can also draw 10. So now you can see that the answer of, let's say, this root node 0, 10 will be actually stored in the 0th row and the 10th column, which we can identify by this cell here. And the answer for the 1, 7, let's say, it will be stored in the 1th or 1st row and the 7th column, which is here. So how does this work? Let's say at first we fill this array with nothing, or let's say an invalid number, let's say -1, because none of the answers can be -1. So we fill this array up with -1, and right now I am not writing it, but let's say any blank cell means that there is a -1 in it. So now when you ask the question, let's say we ask the question for what is the answer for 3, 2, then let's say we haven't calculated the answer yet, but we do calculated it and it's 0. So we go to the cell 3, 2, which is this one, and we see that it's blank. That means the value hasn't been calculated yet. So we calculated it and we realize that it is 0, so we write 0 here. And now when someone else asks, let's say this one, that what is the answer for 3, 2, what we do is we don't calculate the subtree under it, let's say, because we have the answer from this one, which has been asked before, and the answer is 0. And when we have this call again 3, 2, we check in the array, we see that it is not blank anymore, it is written 0 over here, and we return it to the parent, that it is 0. Similarly, let's say, for now it's just an example, let's say we have calculated the value 1 3 and let's say it's 7. I'm saying it again, this value 7 and 1 3 is not related to the tree I have drawn. I'm just using an example. Let's say someone has called 1 3 once and we don't know the value of it, and we have calculated it 7 and written it here. The next time when someone will ask what is the value of 1 3 is, you will just check in the array that it is indeed 7 and it's not needed to be calculated anymore, so we will just return the value from here, that it is 1 and 3 is actually 7. So we are using these pair of numbers, or the index considering and capacity left, as the indexes of this 2D array and stored the answer there, and that is what is called memoization, and this is how we can reduce the complexity of this problem. But about the complexity we will discuss it a bit later. Right now we want to dive into the pseudocode of this dynamic programming solution of this problem, but we will go over the code slowly. At first we will see the brute force version, and then we will actually modify it so that it works with the overlapping subproblems and the memoization. So let's get started with the pseudocode, but at first we need to define some variables. So let's say n is the total number of items in the shop, and we can say that cap is the capacity of the knapsack, p is the array which contains the prices of the items, and w is the array which contains the weights of the items. And the function that is actually going to find the answer for us, let's say the function is maximum profit, and it returns a value, an integer, that is the answer. So the return type is an answer, and let's say the name of the method or function is max profit, and the parameters it's going to take is the total number n. You can pass it as a parameter or you can use it as a global variable. So for now let's think that all of the variables on the left side are global, so we know them. So for one call or for one question you need two variables actually, the index which we are considering and the capacity left. So we are going to mark it as the cap left. And these two are the variables that you need to actually calculate this function. So let's say the function starts here. So remember that this is a recursive function because we are asking the same question again but with different parameters. So any recursive function will actually have a base case. Otherwise this will go on forever. I hope that you know the basic of recursion, and any recursive function must have a base case. If it doesn't have a base case, then it will not know when to stop and it will go on forever. So in this case, the base case is when the index reach at the end of the array. So the total number of items is n. So when the index reaches the number n, it should stop, because otherwise it will go out of the array size and it will get an exception. So when we stop, the condition should be if the index ever goes greater or equal to n, then we have to return the recursive function and the return should be 0. Because whenever you go to this, let's say this position where there is nothing to be considered anymore, you have to return 0 from there, right? There is no profit that you can make from that point. So remember, the question we are asking at any node, let's say on this node, this 2,7 or this 2,5, the question is at this point, considering this element at this index and with this much capacity left, what is the maximum profit that you can make? And that is the answer from its subtree. So when we when we get to the last index, it has to return 0. Now let's say we are not at the last index. So what we can do is that we can consider taking the element at this index, or we can leave it as it is. But you have to think about one more thing. When you can actually take the element at this index, if the weight of this element is less or equal than the capacity left in your bag, only then you can take this element. So we have two choices, let's say. That is, we can take this element or we can leave this element. So we have two choices, so that's why we will introduce two variables. Let's say the first one is ret1 and the second one is ret2. I'm just naming these randomly. Let's say the first one is the one where we will take the element. So for taking the element, we have to consider the condition that if the weight of this element, and that is W index, is less than or equal to capacity left, because otherwise the bag will rip and you can't take the element, only then you can actually take this element, otherwise not. So if we take this element, then we have to do two things. That at first we have to add the price of this element because you're taking this element, and then you have to call this function again because it's a recursive function. You need to call the question again with your index increased by 1 because you're going to the next item, and capacity of your bag reduced by the weight of this item. Because when, let's say, the capacity of your bag is 10 and right now you're taking an element which weighs 5, then you have to reduce the capacity by 5. So this should be the call. You increase the index by 1 and you decrease the capacity by the weight of the item you're taking. And the second choice is to leave the item behind. So in that case we add nothing or we add 0 because we are not taking the item, but we call the function again with the next item in mind because this item we are leaving, so it is out of consideration, but we don't change the capacity left because as we are not taking this item with us, there will be no change in the capacity. So now if you can see that the first variable actually contains the value that will come from taking this element, and the second variable contains the value that will come from not taking this element. So what we have to do is we have to return the maximum. Let's say max is a function which determines the maximum of these two values of ret1 and ret2. Whichever one is better or more, we will return that value. And that is actually the conclusion of this function. It works in such a way that it goes to every index and it considers both ways, taking the item of this index or not taking it. But when taking it, you have to consider that the weight of this item has to be less than the capacity left, otherwise you cannot take it. And if you don't take it, then you consider going to the next item but not reducing the capacity, and then you take the maximum of these two. So this is actually the brute force solution. This is not actually the dynamic programming solution because we haven't done the memoization thing yet. So how do we do it? Well, actually it is pretty easy. So as I discussed, there we will have a 2D array where the row will be the indexes as we have discussed before, and the columns will be the amount. And let's say right now you're considering this row and let's say this column, and that means this cell. So if you calculate this cell for the first time, then you have to calculate it whole. But if someone asks the same question for the second time or the third or the fourth, then you see that it is already being calculated and you can return it from there. So now what we'll use a 2D or two-dimensional array. Let's say the array name is DP, which is a two-dimensional array. And globally it will be filled with minus ones because minus 1 is an invalid value for the answer. So if you see minus 1 in any cell of this array, you can guarantee that this value has not been yet calculated. And if you see something else than minus 1, then you can realize that this value has been calculated. So instead of returning this value directly by comparing the maximum of it, what we do is we store this answer in this cell, dp index cap left, and we actually store this answer, which is maximum of ret 1 and ret 2, and then we return this value. So what we're changing is, before returning a value, we are actually storing it in the array. Now one more thing is left. We are always storing it and returning it, but we also have to check that if it is already in the array or not. So before doing all these operations for any call, here we have to check that if the cell is already written by some value, then we need to return it. We don't have to calculate it. So if dp index cap left is not minus 1, that means it has been overwritten by something other than minus 1. That means it has been calculated. So we return this value directly from here. We don't calculate it again. But if this condition fails, that means it's still minus 1, it hasn't been calculated, and then we do all these operations and store it and then return it. But if it has been overwritten once, then it never gets calculated again. We will just return it from there. And that's how one cell is calculated only once, not multiple times, even though it will be asked multiple times. And that's how we use memoization to reduce the complexity of this problem. The time and space complexity of this problem will be discussed in the next video. This video was on how to actually program this problem with dynamic programming, and this is the complete pseudocode of the 0-1 next problem.